Hello, BC Calc. This is your day 103 notes. Today we are talking about two topics, which I think you'll be pretty familiar with. One being solutions to differential equations, the other being logistic growth. Now, before we get into either of those topics, let's do a quick summary of maybe some of the patterns that you've noticed within improper integrals. So if we have something like the integral from 1 to infinity of the form dx over x to the p, we've seen that in some instances this will converge, and then in other instances this will diverge. So just really quickly, if I were to set this up, we can break this down into the limit as c goes to infinity. We can plug in c as that upper limit there. We're going to integrate x to the negative p dx, which if we use anti-power rule, it's going to be x to the add 1 to this. That's going to be 1 minus p divided by the new exponent. And basically with c as that upper bound of infinity there, right? I'll leave it as infinity for now. We want to think about, okay, the limit as this number goes to infinity. In certain instances, this will converge and approach a number, and in other instances, we'll find that it will diverge. Okay, so it turns out that the instances in which we converge is when this becomes a negative exponent, and that brings us to the denominator here, right? So how is this going to become a negative exponent? If p is bigger than 1. So if p is greater than 1, then we get that the integral converges. Okay, this forces the numerator to a negative exponent. And as x goes to infinity, we know that x to the 1 minus p is going to go to 0. Okay. So therefore, we actually know that it converges to, since this goes to 0, think of pulling this constant out front, 1 over 1 minus p. So 0, and then minus, when I plug in 1 there, it's going to be 1 over 1 minus p, which is going to be 1 over, if we think about just switching the denominator there, it's going to converge to 1 over p minus 1. Okay. So we plug in the upper bound, lower bound there. That's what we'll find it converges to. However, if p is less than 1, we'll find that the integral diverges. Okay, in this case, it's going to force the numerator to be a positive exponent. And therefore, as x goes to infinity, x to the 1 minus p is going to go to infinity as well. So we get this kind of case here that, now keep in mind, this is the integral from 1 to infinity. We've also analyzed other cases from 0 to 1. Basically, if we're looking at 0 to 1, these two cases flip on us. Okay, if p is greater than 1, for integrating from 0 to 1 of something of this form, where it's undefined at 0, this will diverge and this will converge. So that's kind of interesting. And there's a good visual in the textbook that we'll look at in class to illustrate that concept. Okay, but based on our new knowledge, we can very easily determine right now whether or not these converge or diverge, right? Just based on if this is the exponent p, x to the p, if p is bigger than 1 or if p is less than 1. Okay, so in this case, the exponent p is bigger than 1, which tells me right away that I know this converges. Okay, so if I want to know is converge or diverge, we can kind of use this test really quickly to determine whether or not that's true. All right, in this case, this is x to the 1/2, so p would be less than 1 for this one, so we know that this diverges as we find the integral from 1 to infinity. Okay, now p equals 1 is kind of the dividing line. All right, so p equals 1 is kind of a unique case because we know that that's going to represent that if we have 1 over x dx, its integral is ln absolute value of x. It doesn't follow that anti-power rule case, but it does turn out that if p equals 1, this also diverges. Okay, and we could prove that by going through the process. We've proved it before in prior days of notes, but basically if p is less than or equal to 1, we're going to see that it diverges. If p is bigger than 1, we know that that integral from 1 to infinity will converge. Okay, so based on that, let's go ahead and just recap what we've done with some improper integral applications. So on the next page, we have given f of x equals 1 over x. We know that the area from x equals 1 to infinity is infinite, because we just did that a half a second ago. because when p equals 1, we know that the integral from 1 to infinity of 1 over x dx diverges. Okay. So what we want to do is determine, well, even though it has an infinite area under the curve from 1 to infinity, can we determine the volume by taking that region and revolving it around the x-axis? So now if we think about 1 over x from 1 to infinity, okay, so we're looking at this region right here and spinning it around the x-axis, definitely going to be a disk method here. So we're going to do pi times the radius squared, pi from 1 to infinity of 1 over x squared dx, which is pi times the integral from 1 to infinity of 1 over x squared. And we already know the results here. We know that this converges because that value of p, the denominator's exponent, is bigger than 1. So that's the wild thing about this process that we've seen before, that sometimes you can have an infinite area, but when you spin that area around the x-axis, it turns into a finite volume. And that's exactly what's going to happen here. Okay, so we'll introduce a limit, pi limit as c goes to infinity from 1 to c of 1 over x squared dx. Find the antiderivative of 1 over x squared, which is one that maybe you're pretty confident with by now, is negative 1 over x. Okay, plug in your upper and lower bounds. So we get pi. We're going to take the limit as c goes to infinity of negative 1 over c minus, plug in 1, minus negative 1 becomes plus 1. And as c gets bigger and bigger and bigger and bigger, we know that this term right here goes to 0. So therefore, we get pi times 1, which converges to a volume of pi cubic units there. So I know that's kind of a crazy concept, that we can have finite area or infinite areas and finite volumes. And then we even saw extended in our last lesson beyond that to infinite surface areas, meaning we can fill it up, but we don't have enough paint in the world to paint it. Okay. All right, so if there is no antiderivative or the graphing calculator does not help us, then we can use a comparison test. And this is something that will develop a lot more into chapter 9. The two comparison tests that we've looked at so far are the direct comparison test, which again, your textbook will call the domination test, direct comparison test. Okay, so if you can compare it to an easier function that we know the integral for, and we can tell whether or not that converges or diverges, then we'll be able to establish whether or not the function we're trying to integrate is either always greater or always less than the function that we're comparing to, and make some appropriate conclusions from there. We also saw at the very end of the lesson our intro into the limit comparison test, and again, more to come as far as that goes. Okay, so we're looking for the integrals to either converge or diverge, and that also has a property within it such that if the limit as x goes to infinity of the ratio of the functions converges, then we can make some conclusions there as well. Okay. So we're not going to do a lot more with that today, but again, this is just kind of a recap of where we're at up until this point as we head into we're almost at chapter 9. We're very, very close here. Okay, so we are going to take a trip back. This is kind of a little bit of the new stuff today, but we're heading back to a familiar topic on differential equations. So this is actually one of the first differential equations we looked at, and we looked at slope fields related to this. Slope fields will kind of come back in the next few lessons as well. If dy dx equals 2x, then we know that y is equal to, okay, if this is the derivative, take the antiderivative, that would be x squared plus some constant c. And sort of just as another way to think of that, you can swing the dx over to this side, write it as dy equals 2x dx, and then write this as an integral. So this is a good algebraic technique to have to sort of separate the variables and then take the antiderivative of both sides. So this would also very hopefully clearly become y equals x squared plus some constant c. Okay. So then we can find particular solutions given some initial conditions. If y is 6 when x is 1, plug in the initial conditions, we would get that, subtract the 1 over, c is 5. So therefore, the specific solution that contains the point 1, 6 would be y equals x squared plus 5. So today we're going to move on to tougher differential equations, like what if I gave you up to a third order differential here, okay, and I wanted to somehow solve for y in this equation right here. Well, we're not going to quite see something this challenging in our examples. Maybe if you take a course on differential equations, which I'm sure many of you will take at some point in your college careers, that you would be faced with something that challenging. But for today, what we're going to talk about is something called separable differential equations, which is sort of what I did at the very top of the page here. Okay, if you can separate and then go ahead and integrate both sides, you can go ahead and get back to the original equation for y equals. So in this example here, where we have dy dx in terms of y's and x's, let's get all the y's on one side and group all the x's on the other side, and then we'll take the antiderivative of both. So to get the y's over here, I'm going to divide both sides by 1 plus y squared to get dy over 1 plus y squared. And then again, kind of swing the dx over there to get e to the x dx on this side. Okay, and something that looks pretty complicated at the very start, now once I separate the differentials here, if we now integrate both sides, we're going to get back to an equation that says y equals. And these are both antiderivatives we can find pretty easily. We know the integral for dy over 1 plus y squared is just tan inverse of y. And the integral of e to the x dx is e to the x. Now, of course, that when we do indefinite integrals, we need a plus c. You can kind of group all the c's on this side, right? So you don't have to write plus c on both sides. Just kind of group all the constants together over here and write one big plus c. And then lastly, to get y alone, you would take the tan of both sides, right? If you want to get rid of tan inverse, you would take tan of this side and tan of that side to get y equals the tangent of the quantity e to the x plus c. Okay. So then from there, just like we did up above, we can give some initial conditions. So if y equals 1 when x equals 0, we're going to get that 1 equals the tan of e to the 0, which is 1, plus c. All right, so in contrast to what we did up here a minute ago, we were trying to get rid of tan inverse, so we took the tan of both sides. Well, now in order to get rid of tan, you would take the tan inverse of both sides. So tan inverse of 1 would equal, well, tan inverse of tan would just give you a 1 plus c on this side. And it turns out tan inverse of 1 we know is pi over 4. So therefore, the constant c with those initial conditions would be pi over 4 minus 1. So what that brings us to is that our final equation with these initial conditions would be y equals tan of e to the x plus c, where c is pi over 4 minus 1. Okay. So what we're going to do, just to make sure we're really on the right track here, is check to make sure that this all makes sense. And how are we going to check to make sure that this is the correct solution? Well, why don't we just find the derivative, okay, and see if we get back to the original dy dx. So let's see what we get. So if y equals tan of e to the x plus pi over 4 minus 1, let's go ahead and find the derivative here, dy dx. So dy dx would equal, well, the derivative of tan is secant squared. So it's secant squared of this quantity. But don't forget that you then also have to multiply by the derivative of the inside, because we got some chain rule here. So times, just going to be e to the x, right? All the rest of this is constants. So that would be times e to the x. Now keep in mind, the answer that we are trying to get at is that dy dx equals 1 plus y squared times e to the x. And we know what y equals. So do you see where we're headed with this? We know that secant squared, another way of writing that is, if we're trying to get this maybe to look like some tans here, isn't that 1 plus tan squared? So 1 plus tan squared of e to the x plus pi over 4 minus 1 times e to the x. And oh, if tan is equal to y, then tan squared would equal y squared. So this then becomes 1 plus y squared times e to the x. And that shows that, yes, this is the correct answer. That, especially with those initial conditions there, we've also proven that when I find the derivative and get dy dx, we get back to what we had at the very start on the prior page. Okay, so of course we can always check using this technique. In the next example here, I'll encourage you to try this one on your own. Now that you've seen one example here, see if you can find the solution to this differential equation by using a separable differential. Get all the t's on one side, get all the y's on the other. Just be a little bit careful. This should actually say dy dt, not dy dx, so that we don't get confused there. So if you want to fix that for me and then use those initial conditions, we will go over that next time we are in class together. Okay. One of the last things we'll do today is let's do an application that might involve separable differentials. And this is something that we've studied in the past, Newton's law of cooling. So as a reminder, if we let y equal the temperature of an object in a room with a constant temperature of 60 degrees, we're going to go through Newton's law of cooling to figure out if the object cools from 100 degrees to 90 degrees in 10 minutes, how much longer will it take for the temperature to decrease to 80 degrees? Okay, so we know how long it takes to decrease 10 degrees, it takes 10 minutes. How much longer will it take to go from 90 degrees to 80 degrees? So here's going to be the initial setup that's going to help me to figure out the equation that we'll use to determine how much longer it takes here. The rate of change in y is a differential equation between y and 60. It's proportional to the difference. So if you remember setting up applications of this form, the rate of change in y, so dy dt, would equal, it's proportional to the difference between y and 60. So proportional to the difference would be some constant of proportionality k to the difference between y and 60. So here's the differential equation that we're going to set up. And we're going to have to start finding some constants within this such that we can answer the question. Okay. But once you set up the differential equation, hopefully you can see how this is going to become a separable differential. That if I kind of get the y's over to this side, and I'll write k dt on the other side, that we can start our process and find the antiderivative of both sides. Okay, so first and foremost, separate that differential so that this way we can, like I said, find the antiderivative of both sides. So antiderivative of both sides. Antiderivative of y, 1 over y minus 60, that's going to be natural log of absolute value, y minus 60. Okay, so then on this side, the antiderivative k with respect to t is going to be kt. Okay, and we'll put plus some constant. We'll kind of group all the constants over there. And now we have to start finding out, okay, well, what's that constant c equal to? So we have to use some of the initial conditions. So if we look back to the top, the object cools from 100 degrees. So what we know is that t equals 0, that the temperature y is 100 degrees. So let's go ahead and plug that in and really quickly solve for our constant c there. So we're going to get the ln of 100 minus 60 is equal to, and this is going to be k times, this was at time equals 0 plus c. So this really quickly just becomes c on the side, and that would be ln of 40 then. Okay, so what we now know, if I go back, is that we have ln of y minus 60 is equal to kt plus the ln of 40. Okay. And remember, we're looking for how much time this takes, so if we can kind of isolate that variable t, maybe that would be nice. If you subtract ln 40 over here, you can then condense those logs, because if we have log of y minus 60 minus the ln of 40, that would condense to division, so you get y minus 60 all over 40 equals kt. Okay, but notice that we're not really quite at the point yet where we can go ahead and figure out how much longer it takes for the temperature to cool, because we still don't know what k is. What is this constant of proportionality here? Okay. But it turns out we have enough information to find k. Okay. So we know that it takes, in 10 minutes, the temperature y is 90 degrees. Okay, so use the other given information up at the top to now determine the value of k. So if I plug in here, we're going to get the ln of, well, 90 minus 60 is 30, and then 30 divided by 40 is going to be ln of 3/4 on this side. Is going to equal k times 10, or 10k. So really quickly, you're going to wind up getting that k equals the ln of 3/4 all over 10. Okay. And therefore, we know that t is equal to, let's see, well, t would equal, in general, ln of y minus 60 And then we're going to say over 40. We'll get rid of that. And then divided by k. So therefore, the time would be, if I divide by k, it's the same as multiplying by the reciprocal. So 10 times ln of 3/4 times the ln of y minus 60 over 40. Okay, so we finally have this expression where we've gotten the k, the constant of proportionality there. We can figure out how much time it takes to get to any given temperature, y, and what temperature are we concerned with. We want to know how long it takes to get to a temperature of 80 degrees. So if we plug in 80 for y, we're going to get t equals 10 divided by ln of 3/4. And that's going to be times the ln of, well, 80 minus 60 is 20. 20 divided by 40 is ln of a half. Okay, so if you type that in the calculator, it will take approximately 24 minutes. Okay, so I'm just going to shortcut us there. You guys double check me on the calculator. That it takes 24 minutes for this to happen. And of course, we just want to make sure we answer the question correctly. The question said, how much longer will it take? Well, if it took 10 minutes to get to 90, subtract that 10 minutes out, it takes an additional 14 minutes to get to that temperature of 80 degrees. Okay. So kind of a nice application side of things in terms of having a separable differential equation. Okay, separate the variables, take the antiderivative of both sides. You know, this one was just maybe a little bit more complicated because we also had that constant k that we had to determine what that equaled. But once we figure that out, pretty easy application to sub into there. And speaking of cool applications, the last application that we're going to look at, we're going to talk about some grizzly bears tomorrow. We're going to, tomorrow in class, talk about the differences between exponential and logistic growth as a quick recap. And then we'll do this example together about the grizzly bears at a national park. Okay. So that is it for today's lesson on differentials. If you have any questions for me, let me know next time I see you. Have a great rest of your day.